Hello Calc 3, welcome back to another video. This is the video on section 14.2 where we will be talking about limits and continuity in higher dimensions. The nice thing about this video is that it is the last video for which you are required to watch two videos inside of the same day. So for the rest of the course, each day will correspond with one section from the textbook. It might be multiple videos, but at least it will just be one section from the textbook, so that's nice. Okay, so let's get started with this video here. So just as we extended the concept of a limit to vector-valued functions all the way back in chapter 13, in this section we are going to extend the concept of a limit to multivariable functions. So functions that take in 2 or 3 different variables are the ones that we're going to talk about anyways. And then, as you might expect, in section 14.3, we're going to use the limits that we define in this video to define the notion of a derivative for multivariable functions. The same way that for vector-valued functions, we first defined a limit and then use the limit to define a derivative. Okay, so let's move on to limits for functions of two variables. So I'm going to start off by giving an informal definition of the limit, and I'm going to rephrase the idea of the limit multiple times here, just to try and build up an intuition of what the limit is, apart from the rigorous definition. Okay, so for the informal definition, we say that a function f of xy approaches the limit L, where L is just some real number here, as xy approaches the point x0, y0, if the values of f of xy lie arbitrarily close to L for all points xy sufficiently close to x0, y0. If you need to, you can pause the video and read through that a couple of times, but that is the kind of informal idea of what a limit is, and I'll give another informal idea a bit further down below. Okay, so in other words, f of xy approaches the limit L as xy goes to x0, y0 if the distance between f of xy and L becomes arbitrarily small whenever the distance from xy to x0, y0 is made sufficiently small. So there's a way of just rephrasing the informal definition that I gave. There will be another informal definition a little bit further down that I think is the most intuitive, but that's the way that we're going to cap off the discussion of limits. So now here's the technical definition of what a limit is. This is the definition that you have to appeal to if you want to prove that some real value L actually is the limit as xy approaches x0, y0 for some function f. So we say a function f of xy approaches the limit L as xy approaches the point x0, y0, and write limit as xy goes to x0, y0 of f of xy is equal to L if for every epsilon greater than 0 there exists a delta greater than 0 such that for all xy in the domain of f, if the square root of x minus x0 squared plus y minus y0 squared is greater than 0 and less than this delta that we picked, then it implies that the distance from f of xy to L is less than epsilon, or the absolute value of f of xy minus L is less than epsilon. And again, I know that this definition is quite a monster to try and understand in your mind, but hopefully we can make a little bit more sense of it as we go throughout this video. I do want you to notice that the definition is just a generalization of the same epsilon delta definition that was given for single variable functions in Calc 1 and Calc 2. The difference here is that we have to define the distance between points in the plane differently than the distance between real numbers on the number line. So the fact that the square root of x minus x0 squared plus y minus y0 squared is greater than 0 and less than delta means that the distance from the point xy to the point x naught y naught is greater than 0 and less than delta. So we're using a different notion of distance between points. But other than that, the definition is really the same as it was for Calc 1. So now let's give a pictorial description of what this definition is really saying here. So if we pick some epsilon greater than 0, then that epsilon around the limit L is going to give us this open interval, which is over here. This open interval made with the red parentheses on the number line. So that's what happens after we pick some arbitrary epsilon greater than 0. And to show that the limit exists and that the limit is L, we want to find a disk of radius delta that contains the point x naught y naught. So x naught y naught is the point we are limiting to. And we want to find a disk of radius delta centered at that x naught y naught, such that if we take any point xy, so in the diagram here we have that point xy in blue. If we take any point xy inside of that disk and send it through the function f, then that point is going to map inside of that epsilon interval on the line. So let me say that again. We want to find a delta such that if we make a disk of radius delta centered at the point x naught y naught, and we take any point xy inside of that disk, then when we map it through the function f, it's going to map inside of that open interval made by epsilon. So I think this is the most intuitive way to think about it. We're trying to find a space that is small enough around the point x naught y naught such that all of the points inside of that space map inside of the epsilon space on the real number line. So here are some things to know about these limits of functions of two variables. So first off, if we just have the function x, then the limit as xy goes to any point x naught y naught is going to be equal to x naught. And the same can be said about the function y. So the limit as xy goes to x naught y naught of the function y is just going to be equal to y naught. And then the last thing that I'm going to list here that we need to know before we go into the properties of limits below is that if we have a constant function, so the function just maps all points xy to c, then the limit as xy goes to x naught y naught of c is just equal to c, regardless of what constant c we choose. So now that we've given the definition of the limit, let's start talking about properties of limits for functions of two variables. So there's a giant list here. I am actually going to go through each one of the properties and just mention it. So if we let f of xy and g of xy both be real valued functions, and we let capital L, capital M, and K be real numbers, and then we're also going to assume that the limit as xy goes to x naught y naught of f of xy is equal to L, and also that the limit as xy goes to x naught y naught of g of xy is equal to M. Then we have all of these following properties. So the first property is the sum rule, and all of these properties ultimately are just generalized from the same properties we had for single variable functions. But we're going to start out with the sum rule. So the sum rule says that if I take the limit of the sum of two functions, then that's going to be equal to the sum of the limits of each function. So here we have the limit as xy goes to x naught y naught of f of xy plus g of xy is equal to the limit of f of xy, which is L, plus the limit of g of xy, which is M. This is called the sum rule. Okay, the second rule, the constant multiple rule. So if k is just any real number and I'm multiplying it by f of xy, then the limit as xy goes to x naught y naught of k times f of xy is equal to k times the limit of f of xy, so k times L. Next, we have the product rule. In this case, the limit of the product of two functions, so here we're taking f of xy and multiplying by g of xy, is equal to the limit of f times the limit of g. And the quotient rule is very similar to the product rule. If we have f of xy divided by g of xy and we want to take the limit of that function, it's going to equal the limit of f of xy divided by the limit of g of xy, as long as m, or the limit of g of xy, is not equal to 0, because if that were the case, we'd have division by 0, which is not defined. Next up, we have the power rule, which says that if I take my function f of xy and I raise it to some integer power n, then the limit as xy goes to x naught y naught of f of xy to the n is equal to the limit of f of xy to the n. And finally, the root rule. Now if I take f of xy and raise it to the 1 over n, and I take the limit, then the limit is going to be equal to the nth root of L. And there are some conditions that have to be satisfied for the root rule here. So for example, if n is an even integer, then L is going to need to be greater than or equal to 0. Otherwise, we're going to have some kind of square root of a negative number, which is not defined for real numbers. Okay, and with all of these properties, which I've mostly just listed here for your convenience so that you can reference them, we actually get the following fact. So for polynomials and rational functions, remember that rational functions are just functions that look like fractions, and where the top is a polynomial and the bottom is a polynomial, kind of like the function that I have here in this example. So for polynomials and rational functions, these rules that I just listed above imply that the limit as xy goes to x naught y naught of f of xy is equal to f of x naught y naught as long as f of xy is defined at x naught y naught. In other words, remember from Calc 1 that if you took the limit of a polynomial or a rational function and you took the point that you were limiting to and you could plug it into the function, and if that value that you got when you plugged it in was not 0 over 0, as long as it was a determinant form, then the limit was going to equal the value you got when you just plugged it in. So the examples that I have below are examples of just that. So first we're going to take the limit as xy goes to 0, 1 of the function x minus xy plus 3 divided by x squared y plus 5xy minus y cubed. And we're going to start off, because this is a rational function, let's see what happens if we just plug in 0, 1 for our function. What value do we get? So we get a 0 minus 0 times 1 plus 3 over 0 squared times 1 plus 5 times 0 times 1 minus 1 cubed. Again, this is just from plugging in 0 for x and plugging in 1 for y. And if we simplify that, we get 3 divided by negative 1, which is equal to negative 3. So because the function is defined at the point 0, 1, and it's a rational function, then the limit as xy goes to 0, 1 is just going to equal whatever value we get when we plug in 0, 1 to our function, which is negative 3. And then another example of this same concept. So here we have the function is the square root of x squared plus y squared, and we're going to take the limit as xy goes to 3 minus 4. Then we can start off by just seeing what happens when we plug in 3 and minus 4 for x and y respectively, and we end up getting the square root of 25, which is equal to 5. So because the function is defined when we plug in 3 and negative 4, then the limit as xy goes to 3 and negative 4 of our function is going to be equal to 5, the value we get when we plug in 3 negative 4 to the function. Okay, so now that we have those examples behind us, we are going to move into some examples that are significantly more difficult. And I know that they're significantly more difficult, so I understand if you have trouble following along here. I think that's completely normal. Also know that I don't think I'm going to end up being super strict with these kind of proofs showing that a limit exists or does not exist, or showing that a limit is some value or not some other value. But I do want to see that you are attempting these kind of problems. And I can tell you that I'm going to give you a problem at least where you have to prove that the limit doesn't exist at some point for some function. And we'll get to some methods below that you can use to show that limits don't exist. But you can at least count on me asking you at least one question where you have to show that a limit doesn't exist at a certain point. But in this example, we're going to show that a limit does exist, and we're going to find what that limit is. So we're going to find the limit as xy goes to 0, 0 of 4xy squared divided by x squared plus y squared if it exists. And spoiler alert, the limit does exist, which we will show below. So first, we want to note that if we approach the value 0, 0 along the line x equals 0, then the value of x is 0 for all y not equal to 0. So first off, what do I mean by approaching the point 0, 0 along the line x equals 0? Well, if you think about all of the points in the plane, and then you think about the origin inside of the plane, remember that as we take the limit, we're taking points and we are going to be approaching the limit point, which in this case is the origin. But we can approach that limit point, the origin, from all kinds of different directions. Maybe we can approach it along the y-axis or along the x-axis, or maybe we can approach it along a different line or even a parabola. We have all kinds of different options in terms of what direction we are going to approach the origin from. And when I say along the line x equals 0, it means that we are going to approach it along the y-axis. So we're going to get closer and closer to the origin as we're moving down the y-axis or up the y-axis towards the origin. So if we're approaching 0, 0 along the line x equals 0, then the value of x is going to be 0 for all of the points on that line. And for that reason, if you would take x equals 0 and plug it into our function up here, you find that you get 0 over y squared. And because we are approaching the point 0, 0, we're assuming that y is not equal to 0, in which case the function along the line x equals 0, where y is not equal to 0, is going to equal 0. So the function is going to equal 0 along the line x equals 0, as long as y does not also equal 0. But what this means is that the limit, if it exists, along the line x equals 0 is going to equal 0. And so if the limit exists at all, then the limit has to equal 0. So this refers to something I don't think I've said yet, but if you have a limit of a multivariable function and the limit does exist, then if you approach the limit point from all possible different paths inside of the plane, then you have to get the same limit regardless of the path that you approach the limit point from. So because we got the limit is equal to 0 when we approached along the line x equals 0, it means that if the limit exists, then the limit has to equal 0. It doesn't necessarily mean that the limit exists. For example, I could approach along the line y equals 0, and we could find that the limit along y equals 0 gives us a different value. And if that was the case, then the limit would not exist. But we know that if the limit does exist, then the limit has to equal 0. So now we have to show that the limit actually exists, because we know that if it exists, then it has to equal 0. And the only way we can do that is by using the definition of the limit. So this is where the example is going to get pretty difficult if you haven't seen this idea before, which I'm assuming you haven't, or maybe you've touched on it a little bit in Calc 1 or Calc 2. But to do so, we're going to use the definition of the limit, And so we let epsilon be some number greater than 0. And to show the limit exists, we want to find some delta greater than 0 such that if the point xy is such that the square root of x squared plus y squared is between 0 and delta, then it implies that the absolute value of f of xy minus 0 is less than epsilon, because remember 0 is going to be the limit point if this limit exists. So now the absolute value of f of xy minus 0 is of course the same as the absolute value of f of xy, and then we can plug in the function for f of xy. So that's 4xy squared divided by x squared plus y squared. We're still taking the absolute value of that. And now we can make that look a little bit nicer, because remember x squared plus y squared is always going to be greater than or equal to 0. So the absolute value of x squared plus y squared is just equal to x squared plus y squared. Y squared is always going to be greater than or equal to 0, and 4 is of course greater than 0. So we can actually simplify it to this expression here, where we just keep the absolute value around the x. And so we want a delta greater than 0 such that if the square root of x squared plus y squared is between 0 and delta, then 4 times the absolute value of x times y squared over x squared plus y squared is less than epsilon. Again, this is just the definition of the limit here. Well, we can note that x squared plus y squared is going to be greater than or equal to y squared, regardless of what x squared or y squared we choose, because x squared and y squared are both greater than or equal to 0. And so this implies that 4 times the absolute value of x times y squared over x squared plus y squared is less than or equal to 4 times the absolute value of x times y squared over just y squared. Because remember, x squared plus y squared is greater than or equal to y squared, implying that this guy has to be less than this guy. And now, as long as y is not equal to 0, then this expression is equal to 4 times the absolute value of x. And that's okay, because we're assuming that y doesn't equal 0, because the limit point is 0, 0. Also, the absolute value of x is equal to the square root of x squared, and that's going to be less than or equal to the square root of x squared plus y squared for all y. Because again, y squared is always going to be positive, or greater than or equal to 0, I should say. And for all of these reasons, we're going to let delta equal epsilon over 4. And I think the reason we let delta equal epsilon over 4 is going to become clear now, once we go through these next couple of steps. So, assume that we have some point xy, and xy is such that the square root of x squared plus y squared is between 0 and epsilon over 4. So here we've let delta equal epsilon over 4, and we need to show that the absolute value of f of xy minus 0 is less than epsilon. That's our ultimate goal here. Then we can write the absolute value of f of xy minus 0 is equal to, ultimately, this 4 times the absolute value of x times y squared divided by x squared plus y squared. And we already said that that's going to be less than or equal to 4 times the absolute value of x. And we also said that because the square root of x squared plus y squared is less than epsilon over 4, and because we already said up here that the absolute value of x is less than or equal to the square root of x squared plus y squared, which is less than epsilon over 4, we can use this inequality to say that 4 times the absolute value of x is less than epsilon. And so this ultimately means then that the absolute value of f of xy minus 0 is less than epsilon. So we picked a delta, which happened to be epsilon over 4, such that if the distance from our point to the origin is between 0 and epsilon over 4, then the distance from f of xy to 0 is less than epsilon. And for this reason, by definition, the limit exists and the limit is equal to 0. So I am completely aware that for the majority of people, this proof that I just gave to say that the limit is equal to 0 is super foreign and probably difficult to follow, and that is okay. I would actually just encourage you to go onto Blackboard and find my lecture notes and read through this proof a couple of different times until you feel comfortable, like you understand generally what's going on inside of the proof. So the idea is we pick some epsilon greater than 0 and we need to find a delta greater than 0 such that the conditions for the definition of a limit are met. That's the general idea. And then the question is, what are the little nitpicky things that we have to do to make sure that that we can actually find that delta? So read through the proof that I have multiple times, and also email me questions about the proof or things that you don't understand if you find that you're really struggling to understand it. I am going to give probably at least one homework problem where you're going to be evaluating or proving that a limit exists for a function like this. So you're going to get a little bit of practice, but not too much. So email me if you have any questions or there's confusion related to the proof that I just gave. Okay, so now that we've talked about limits for multivariable functions, it makes perfect sense to move on to the idea of continuity, which is exactly what we moved on to with vector-valued functions, and it's what we moved on to when we introduced limits for single-valued functions back in Calc 1. So the definition of continuity for functions of two variables and ultimately any multivariable function mimics the definition for functions of one variable. So I'll just give the definition here. It should be familiar. A function f of xy is continuous at the point x0, y0 if the following three conditions are satisfied. So 1, f has to be defined at the point x0, y0. It has to make sense to put the point x0, y0 into our function. The second condition, the limit as xy goes to x0, y0 of f of xy has to exist. That's the second condition. And then the third condition is that the limit as xy goes to x0, y0 of f of xy is actually equal to f of x0, y0. So the limit is going to equal the value we get when we plug in the limit point to the function. So if all of these conditions are satisfied, we say that the function is continuous at the point x0, y0. And more than just that, we say that a function is continuous just generally if it's continuous at all of the points in its domain. So because of the properties of limits of functions of two variables, so the properties that I listed in this box up here, because those properties hold, we can say that sums, differences, constant multiples, products, quotients, and powers of continuous functions are also themselves continuous whenever they're defined. So what that means is that if I have a continuous function and another continuous function and I add them together, I get a continuous function. If I subtract them, I get a continuous function. If I multiply them by a constant, I get a continuous function, and so on for all of these properties here. And in particular, polynomials and rational functions of two variables are continuous whenever they are defined. So that's an interesting thing to note. Make sure you remember that because that's an easy way to just say right off the bat when a polynomial or rational function is continuous. Okay, and now let's move on to something that I alluded to before when I gave that example of proving a function had a limit. We have what is called the two-path test for the non-existence of a limit. So this test is only going to give us the non-existence of a limit. It is not sufficient to give us the existence of a limit. And the test says this: if I have a function f of xy, and if that function has different limits along two different paths in the domain of f as xy approaches x0, y0, then the limit as xy goes to x0, y0 of our function does not exist. So let me say that again. If I have a function f of xy and I approach a limit point from two different paths that are in the domain of my function, and the limit that I get as I approach along different paths, if these limits do not equal one another, then the limit as xy goes to x0, y0 of my function does not exist. So the limit does not exist at that point if this is the case. But again, this test is not sufficient to show that a limit does exist. So if I just pick two arbitrary paths and I approach my limit point along these two different paths, and I find that the limits along the two different paths are equal, it is still very possible that the limit will not exist for that point. It's not sufficient to show that the limit exists along two different paths to say that the limit exists in general. To show that the limit exists in general, you really do have to go back to the definition of the limit, just like I did in the example that I showed previously. So let's give an example where we are using this test. We want to show that the function f of xy is equal to 2x squared times y divided by x to the fourth plus y squared has no limit as xy approaches the origin, or the point 0, 0. So we want to find two different paths such that when we approach the origin along these two different paths, our function has a different limit along the different paths. So let's start off by plugging in 0, 0 to our function, because we should notice that our function is a rational function. And for that reason, if the function is defined at the point 0, 0, then the limit is going to exist. So we already talked about that property of rational functions before. But the problem is that if we take the point 0, 0 and we plug it into our function f, we get 0 over 0, which is an indeterminate form. So the function is not defined at 0, 0. So we're going to have to do a little bit more investigation to see whether the limit exists or not. So we are actually going to examine the limit as we approach the origin along parabolic curves. So in the other example, we approached the origin along the line x equals 0, and I talked about approaching the origin along the line y equals 0, so going down towards the origin. In this case, we're going to talk about approaching the origin along parabolas. So if I draw a plane here, and then the origin is going to be at the center, of course, then we are going to approach the origin along curves that look like this. Down towards the origin, we can go down towards the origin from this direction, we can go towards the origin from this direction. The point is that all of the directions or the paths that I'm using to get to the origin are parabolas. And so these curves have the form y equals kx squared generally, where k is just some real number. And we are not including the point x equals 0 because that's our limit point here. So consider along the curve y equals kx squared, where k is just some arbitrary real number, we have that f of xy is equal to f of x kx squared. So here we've taken kx squared and we've substituted it for y. And then if we plug that into our function, we get 2x squared times kx squared as our numerator. And then on the bottom, we have x to the fourth plus k squared times x to the fourth. And we can simplify this a little bit. We get 2 times k times x to the fourth in the numerator, and we get in the denominator a 1 plus k squared times x to the fourth. And again, we've assumed that x is not equal to 0 because we're approaching the origin. So we're going towards 0, 0. And so we can cancel this x to the fourth on the top and the x to the fourth on the bottom that shows up in our function here. Let me just draw that. So we can cancel these two x to the fourths. And so the function f of x kx squared ends up just equaling 2 times k divided by 1 plus k squared. And so along the parabola y equals kx squared, the function has a constant value, namely 2k divided by 1 plus k squared, meaning that the limit along the curve y equals kx squared is equal to 2k divided by 1 plus k squared. And of course, this value is going to change depending on what k we choose. So we can just choose two arbitrary parabolas. Say we choose the one where k equals 1, so that y equals x squared, and then we can choose the one where k equals 2, so that y equals 2x squared. And if we approach the origin along these two different curves, then we get different limiting values. And because of the theorem that we have above, this two-path test for the non-existence of a limit, because we get two different limiting values as we approach along different paths, it implies that the limit at the origin does not exist. So we can conclude that the limit of our function as we approach the origin doesn't exist. And I will give a homework problem, at least one of them, where you're going to use the two-path test like this as well. So the last thing for this section, I just want to give a remark, and that remark is that the composition of continuous functions is also continuous. So remember up above, I said that because of the properties of limits of functions of two variables, we have that sums of continuous functions are continuous, differences are continuous, products of continuous functions are continuous. I didn't list here composition of continuous functions, but it is the case that the composition of continuous functions is continuous. And let me just make this a little bit more explicit here. So if we have a function f of xy, and that function is continuous, and we also have a function g of x, notice that this is a single valued function, so it takes in one value and outputs one value, then the function g of f of xy is also going to be continuous, where g of f of xy is a single valued function, because f of xy is going to correspond with one value that gets inputted to g and then outputs one value. So that's the end of the material for section 14.2. I know that this material is dense and difficult, but I will be giving some homework so that you can practice, and that should be up on Blackboard sometime on Wednesday, I believe. So again, email me if you have any questions about this material. I am happy to help.